We're going to be covering alcohols, ethers, and thiols in this video as a continuation of our organic chemistry unit. So I'm going to be introducing 3 new organic compounds and 3 new functional groups that we haven't seen before. Ethers are molecules that have an oxygen bonded to 2 carbons within the carbon chain. Here in this picture, we can see that the oxygen atom is represented by this red molecule in the figure. Next we have thiols. Thiols are any organic molecule that has a sulfhydryl group bonded to the main carbon chain. A sulfhydryl group is simply composed of 1 sulfur and 1 hydrogen. And in this diagram we see this group represented here, where the sulfur is in yellow and the hydrogen is in white. Next we have alcohols. Alcohols are pretty similar to thiols. They have a hydroxyl group bonded to the parent chain, and that's simply an oxygen and a hydrogen bonded together. Here we can see that this molecule here represents the alcohol group, with the red atom being the oxygen and the white atom being the hydrogen. So I've depicted these molecules in order of increasing priority from left to right. And remember, depending on the priority of the functional group, the root of the word will change to match that of the group with highest priority. Between these functional groups here, if we were to see them on a chain, just realize that alcohols, out of the 3, would have the highest priority. So up first we have alcohols. Alcohols are organic molecules that contain at least 1 hydroxyl group. And so just to clarify, a hydroxyl group has an oxygen bonded to 1 hydrogen atom. Depending on the structure, there are 3 different ways that alcohols can be classified. At first we have primary alcohols, and these are simply alcohols where the hydroxyl group is bonded to a carbon that is only bonded to 1 other carbon in that chain. So essentially, it's going to be bonded to one of the end carbons. Generally, these alcohols can be drawn as such, where we see that this carbon right here is bonded to 1 other carbon. Next we have secondary alcohols. Secondary alcohols are where the hydroxyl group is bonded to a carbon that is bonded to 2 other carbons in the carbon chain. They can be drawn as such. Where we see this carbon is bonded to 2 carbons at both sides. Finally, we have tertiary alcohols, and this is where the hydroxyl group is bonded to a carbon that's bonded to 3 other carbons. Typically, this indicates the presence of an alkyl group bonded to that same carbon, and they can be drawn as such. Where we see that there are 3 other carbons bonded. So when we're naming alcohols, there are 2 different methods that we might take depending on the priority of the hydroxyl group within that molecule. If alcohol happens to be the functional group with the highest priority, then the root of the word, or how we're going to finish off the name, becomes OL or OL. The steps for naming are very similar to what we've already established in previous videos, where we're going to start numbering the carbon chain this time such that the OH group is bonded to the carbon that has been assigned the lowest possible number. So if we're working with a polyalcohol, which means that there's more than 1 hydroxyl group present on the same molecule, then we must include a plural prefix before the OL ending. And just a reminder, these are our di, tri prefixes that we've encountered in the past. Now, it is also possible that alcohol groups can be found in the cyclic and aromatic hydrocarbons. And if this is the case, then the rules for naming follow what we've established before. But now we just assume that the hydroxyl group is bonded to carbon number 1, and we begin numbering from there. Now, it is also possible that the hydroxyl group will be on the same chain as another group of higher priority. We're going to see more of these in later examples. But if that's the case, then we would treat the OH group as a substituent group instead, where we'd write down hydroxyl to represent it in our IUPAC name. The hydroxyl group would be included with all the other substituent groups if there are any, and the naming rules would proceed as normal. Now we have some examples. We're actually going to start with the one on the left. So first, let's recognize here that we have a cyclic structure. Since it's cyclic, we know that we're going to use that cyclo prefix in our name to indicate its structural nature. Next, we want to identify what substituent groups are bonded to this ring. We see here that we have a hydroxyl group at the top and kind of at the bottom right. So we have two hydroxyl groups. There's no other substituent groups and no other functional groups of higher priority that we have to worry about. So we know that the ending for this word is going to be the OL ending as to represent the alcohols, which are the highest priority. Now we can number the carbon chain in the correct fashion. We're going to want to give carbon 1, assign carbon 1 to one of the carbons bonded to either of the OHs. Whichever OH you give carbon 1, it doesn't matter. It's going to end up with the same result. So I'm just going to assign carbon 1 to the OH group at the very top. And you're going to want to number it in the direction so that the next substituent and the next OH is going to be bonded to the lowest possible carbon. So if we number it clockwise, we see here that there is one OH bonded to carbon 1 and another OH bonded to carbon 3. And so just like that, we have enough information. I'm just going to write this down too, that we also have 6 carbons in our parent chain. We got that from numbering it. So we know we're going to use that hex prefix to represent our parent chain. So I'm just going to go ahead and assemble the name now. No substituent groups to worry about, so we can skip right over that. We have cyclo at the beginning to represent that it's cyclic. We have hexane, which represents our parent chain, parent ring here. And then we want to indicate the position for both hydroxyl groups, which is at 1 and 3, diol. Remember, we need that di prefix because we're dealing with 2 of the same molecule here. So the final name would be cyclohexane 1,3-diol. We're going to move on to the example on the right now. Here it's no cyclic structure, we have a branch structure instead. So we can go ahead and identify what substituent groups are attached to the main parent chain. We first see that we have a hydroxyl group right there, and we also have an ethyl group bonded to the same chain. Now the hydroxyl group is going to be of the highest priority. It will always take priority over an alkyl group. So now we know that this has the highest priority. We're going to want to number it so that the hydroxyl is assigned to the carbon with the lower number. So if we actually start numbering it from right to left, then we would end up with the desired result. Hydroxyl would be bonded to carbon 1 as opposed to carbon 5 if you did it the other way around. And so we'll begin numbering in that direction. We also see that this ethyl is bonded to carbon 3, OH bonded to carbon 1, and so we can actually just go ahead and start assembling our final name. So we want to write in our substituent groups first. So 3-ethyl, its placement and what it is. Then we're going to want to write in the prefix for the parent chain. Here we see that we have 5 carbons, which means we're going to use a pent prefix. It's going to be pentane. There's no double bonds present, so we use that ane ending. And then we want to indicate the position of the OH group and indicate the proper ending. So we have 3-ethyl pentane 1-ol. So we're going to do one drawing example for cyclohexane 1,3-diol. So there's a lot we can actually decipher from this name. I know it looks a little complicated, but let's break it down. First, we see that we have cyclohex. This means that we're going to have a 6-membered carbon ring. So we can just go ahead and draw that in here. That's going to act as our parent structure. And let's keep going. We also see here that we have that ENE included in the name, which indicates that there is a double bond present in the structure. at the 4th position. So I'm going to number the carbon chain in this fashion. This is going to be carbon 1, 2, 3, 4, 5, and 6. We know that the double bond is going to be at carbon 4. So I'll just draw another line, and there we go. That indicates that there is a double bond there. And finally, we see here that the functional groups that are present are going to be 2 alcohols, as that OL ending is the ending for alcohols. And they're going to be present at the 3rd carbon and 1st carbon position. So, according to the numbers we've written here, I can draw a line straight up from carbon 1 and 3 that is bonded to 2 OH groups. And there we've assembled the final structure for cyclohexforenone 1,3-diol. So now let's consider the properties of alcohols. In a hydroxyl group, we have a hydrogen atom bonded to a highly electronegative oxygen atom. As a result, these molecules actually exhibit hydrogen bonding, which is the strongest type of intermolecular force, so we can classify them as a polar substance. Additionally, these alcohols can form these bonds with surrounding alcohols. So we see that there's a partial negative charge on oxygen, so it can form a bond with the partial positive charge of a hydrogen on a neighboring alcohol molecule. Similarly, the hydrogen on the same molecule can form a partial negative charge with an oxygen on another neighboring alcohol. As a result, this increases the amount of energy that we need to input into a system in order to dissociate these bonds. So we see that alcohols typically have fairly high boiling points and are water soluble. However, this tends to decrease with chain length, since as you increase with the chain length, you are essentially increasing the size of that nonpolar region. So we see that these longer alcohol chains have lower polarity levels and are less soluble in water than their shorter counterparts. Now, all alcohols have that polar region from the OH group and a non-polar region, and this allows them to dissolve both polar and non-polar substances because like dissolves like. So as a result, alcohols make for really good solvents. Alcohols can also undergo a variety of reactions. I'm going to focus in on 2 of them. First, we can see that alcohols can be formed through a hydration reaction, which is a type of addition reaction. In a hydration reaction, we can extract from the name that we are going to be reacting a molecule with water. To form an alcohol, we have to react one alkene with a water molecule. And this is going to form 2 possible alcohol products, but we're going to follow Markovnikov's rule to determine the major product in this situation. Remember, the hydrogen atom from the water is going to bond to the carbon that is bonded to the most amount of hydrogen atoms already. So out of the 2 of them, we would determine that this is the Markovnikov product or major product. So alcohols can also undergo a dehydration reaction where a hydrogen and a hydroxyl group is removed from the reactant, resulting in a smaller, sometimes broken apart molecule and a water group. So this can be thought of as the opposite of a hydration reaction. So in this type of reaction, we will see that the alcohol will undergo a dehydration reaction with the help of sulfuric acid. Now, sulfuric acid acts as a catalyst in this situation, and a catalyst is essentially any chemical that helps and speeds up a chemical reaction, but is not consumed in the process. So, this reaction will produce an alkene and a water molecule. Now, if we're working with secondary and tertiary alcohols, it is possible that we could also produce more than one alkene, but we're not going to focus on that in this course. So now we're on to ethers. Ethers are organic compounds that contain an oxygen bonded to 2 carbons in the carbon chain. So we can say that the oxygen has kind of been inserted right into that chain. To form an ether, we can react two alcohols together in a condensation reaction. In general, condensation reactions will react two smaller compounds together to form one large compound, and a water molecule is also going to be produced during this reaction. Now, in the reaction below, we are going to react methanol with an ethanol, two fairly basic alcohols, and with the help of H2SO4, which acts as our catalyst, this reaction produces methoxyethane, our desired ether, and also a water molecule. So now we'll consider ether's properties. Oxygen is a fairly highly electronegative atom, so because of that CO bond, this molecule does exhibit dipole-dipole forces, not the hydrogen bonding that we saw in alcohols, so it is slightly polar, but not as polar as an alcohol would be. For ethers, we'll also have a fairly high boiling point, but again, it will be lower than an alcohol of the same size. And similar to alcohols, it also possesses a polar and nonpolar region, so it can act as a very good solvent. So when we're naming ethers, there are two different methods we could take. The first method, which is also the IUPAC method, will use the word oxy within the name. First, we have to examine the length of the carbon chains on both sides of the oxygen. The longer or more complex chain will be used as the base of the word. To start the name, we will use the prefix for the shorter carbon chain. Then we attach it to the word oxy, and then attach the full name for the longer carbon chain afterwards. If we're working with a carbon chain that's longer than two carbons for the more complex side, then we have to indicate what carbon it is attached at. And that is going to be indicated right at the very beginning before we even put the prefix for the shorter chain. So we can also name these compounds a different way. For the second method, you would write out the name of both alkyl groups on each side of the oxygen in alphabetical order, and then end the name with the word ether. If the alkyl groups happen to be the same, then we are going to use the di prefix instead of writing them out twice. Now, I'm not going to be focusing on using this naming convention. I'm going to be focusing on the IUPAC convention, but for some quick examples, if we see this molecule here, it would be called ethyl methyl ether. And in the second molecule here, we see we have two carbon chains of equal length, so this one would actually be called dimethyl ether instead. So I have two examples for ethers. We're going to start with the naming example on the left. So right in the middle, we have our oxygen, so we know that this is an ether compound that we are dealing with. And now we want to determine how many carbons there are on both sides of the oxygen molecule. So I've gone ahead and labeled where each carbon is. So on this side, we see that there are 4 carbons in the chain, whereas on this side, we see that there's only 3 carbons in the chain. This will compose of the base of the name, and this will be the beginning of the name because it's our shorter chain length. Now, we also have to number the 4 carbon chain. Since it's longer than 2 carbons, so we have to indicate at which carbon the oxygen is bonded to. If we start numbering it so that it's bonded to the lowest possible carbon number, the oxygen is, then we would have it bonded to carbon 2 in this chain. So we can go ahead and start assembling the name. First, we have to indicate at what carbon this 4 carbon chain is bonded to. We just write 2 there. We have that 3 carbon chain that we're going to write first because it's shorter and less complex. And remember, the prefix for 3 is prop. We write the word oxy because it's an ether. And then we end it with butane because our longer, more complex chain is 4 carbons long. And then our final name would be 2-propoxybutane. So let's move on to our next example, which is 3-ethoxypentane. So let's decipher this name a little bit more. Here we see that we have an eth, which is short for an ethyl, so a 2-carbon chain. And we also see that we have a pentane, so we also know that we're dealing with a 5-carbon chain, and those are going to be the 2 chains on both sides of the oxygen. Now we have this 3 at the beginning, and this 3 corresponds to the pentane. It indicates at which carbon in the pentane chain that the oxygen is going to be bonded to. So I'm just going to start by drawing the oxygen, and then we can just kind of draw the carbon chains based off that. On the left side, I'm going to draw my shorter ethyl chain. So here's 1 carbon, here's 2 carbon, and that's finished. Now on the right side, we're going to draw our pentane. Remember, it's bonded at the 3rd carbon position. So we can draw, we'll just assume this is carbon 3. Up here we can draw carbon 2 and 1, and then at the bottom would be carbon 4 and 5. And there we have the complete structure for 3-ethoxypentane. So the final group we're going to look at are thiols. Thiols are organic molecules that contain a sulfhydryl group bonded to the parent chain. The chemical formula for these groups is similar to hydroxyls. It's a sulfur bonded to a hydrogen atom. So thiols are well known for their distinct odors. When you think of the smell of skunk spray or even the smell of garlic, these aromas can be attributed to the presence of a thiol. Actually, we tend to add thiols to many different natural gases since we can smell if there are any gases present this way, because naturally many of these hydrocarbons, they lack any sort of odor. So to name thiols, there are again 2 different routes we might have to follow, similar to an alcohol. If the sulfhydryl group is of the highest priority on that chain, we must include thiol as the base of the word. If there is another functional group of higher priority on the same chain, then we'd write it as a substituent group, and we write down sulfanyl instead. So to end off this lesson, we have 2 thiol examples. We're going to start with the name example on the left. So we can identify the substituent groups present here. We see that we have a sulfhydryl group, and we also have a methyl group present. Now, the sulfhydryl group has the highest priority on this chain. It's, again, going to override any alkyl group. So we want to number the carbon chain such that the sulfhydryl group is assigned to the lowest possible carbon number. That would happen if we started numbering from left to right, where the sulfhydryl group would be bonded to carbon 2, and the methyl group would then, as a result, be bonded to carbon 3. From this, we see that we have 6 carbons in the parent chain, which means that we are going to use the hex prefix when we're assembling our name, and we can actually go ahead and start doing that. So first, let's indicate all our substituent groups. We have our methyl at the 3rd position. Now we're going to write in hex, hexane, because there is no double or triple bond present, so we write the AN too. And then we indicate the position of the sulfhydryl group, and thiol, because it is a thiol. So the final name would be 3-methylhexane 2-thiol. Now we're going to do a quick drawing example. So we have here cyclobutane 1,2-dithiol. So from this name, well, we can see that we have cyclobutane, which means we have a 4-membered carbon ring. So down here, I'm just going to draw in a square. That's going to be our butane ring. And we see that there's no substituent groups preceding cyclobutane, but there are 2 thiol groups included at the very end. And they are at position 2 and 1. So I'm going to start numbering the carbon ring from this corner over here in the clockwise direction. So at carbon 1, we would draw one sulfhydryl group, and at carbon 2, we would draw the second sulfhydryl group. And there we've assembled the structure for cyclobutane 1,2-dithiol. And that is everything for today's lesson.